Here's a definition you read about in the early reading, and that is the one of network. The network means the sum of all the works done by all the forces that act during an object's motion. So we've seen that lots of forces can act on an object as it moves from an initial to a final position. The net work, and we're going to denote W, work by W, and the subscript net means just add them all up. It means the sum of all the works done by all external forces acting on the object or the system during the motion. And in this case, some of the works might be positive, some might be negative, some might be zero, but we just add them all up with their signs. So if we orient the x-axis along the direction of motion, the network would be, let's imagine we have 9 different forces acting on it, so n is 9 here. We do the force 1's x component times delta x plus the same thing for force 2 all the way up to force 9. That's the network, just add them all together. There is a common factor of delta x in each one of these terms, so I can factor that out on the right and put some parentheses around all the forces. And what's in the parentheses is nothing other than the net force x component acting on the object as it moves. So here's a different way of writing it. It just feels a little bit different. The first way is sometimes a useful way to think about it. Add up all the works. Sometimes this is a useful way to think about it. Just take the net force and calculate the work that the net force does on the object during the motion. Either one is the same exact thing. Let's do a voting question now. Here we've got a similar kind of situation we had before. A heavy box moves along a rough floor with a constant force being exerted through a rope that's attached to the box in the direction that's shown. So it's a little bit up and to the right. Along the way, we're exerting a constant force. It passes points A and B. And what is the net work done on the box in going from A to B? Is it positive, zero, negative? Impossible to determine. It could be positive or zero, or could it have any one of the 3 signs? I'm not going to give you too much time to think about this one because usually people make an assumption about this question that's not given up above. It's not like, or we don't necessarily know it's like the case that we did before where we were pulling at constant velocity. It didn't say we were using, it was being pulled at constant velocity. Rather, the force being applied here is constant, and it could be accelerating the whole time it goes in this direction, or it could be being pulled at constant velocity, or it even could be slowing down as it goes and passes A and B. In other words, there's a friction force that's slowing it down, and I'm not quite pulling hard enough to overcome it, so it's going slower and slower and slower as it goes closer and closer to a stop as it passes A and B. So, if it's accelerating along this direction as it passes A and B, then the net force has to be along that direction, and that means the x component of the tension force has to overcome the friction force, okay? And that means that we're going to have a greater positive work done by the tension force than the negative work done by the friction force, and in that case, the network would be positive. In the case where it's moving along at constant velocity, the x components of the force is balanced, and so we have equal and opposite works done by the string and the friction force. Or if it's slowing down, then the friction force has to be bigger than the x component of the string force. And so you have a bigger negative work done by it than the positive work done by this. So it's impossible to determine. Maybe that's a trick question. Similar situation, I imagine I have a book in the palm of my hand, and I am lifting it up with my palm underneath the book at a constant velocity, just raising it up very uniformly to a higher position, and moving at a constant speed during this whole time. In that case, the net work done on the book as it goes from here to here would be 0 because the net force on it is 0, and if I add up this force would do a positive work, but this one would do an equal amount of negative work as it goes up in this direction. This force is along the direction of motion, and this one opposite the direction of motion. Or the net force is 0, and therefore the net force times delta x, if I align my x-axis along this direction, would be zero net work. If the book instead is speeding up as I raise it upward, then my hand force has to be bigger than the gravitational force. That means the net force is upward, and the net work would be positive in that case. So there's a positive net work done as it speeds up in that direction. Similarly, suppose I'm slowing it down. It's getting closer and closer to rest as it rises upward with my hand underneath it. Then the hand force has to do less than overcome the gravitational force in order to have a net acceleration downward. And that means we have a bigger negative work done by gravity than the positive work done by my hand, or a net force that's downward, and that gives a net work that is negative. Net force that's down, displacement is up. Okay? Let's do a short note on how to calculate force work for non-constant forces. Everything we've done so far assumed that the forces being applied to the object were constant from initial to final state, but now let's relax that a little bit, and this is something we won't use too much during the class, but you might see a homework problem or two that deal with it, and you certainly will read about it in the book. So let's imagine an object moves along the x-axis while a net force on it is changing. In other words, the forces are acting or changing, so the net force is changing. And let's plot the net force exerted on it with this red curve as a function of x. So as it moves along x, here the net force has a negative x component. That means the net force is in the negative x direction. Here its x component is positive of the net force. So the net force is in the positive direction. Here it's negative again, then positive. Okay, so that's shown by the red curve. And to analyze or connect it with what we've already done, we're just going to consider a very tiny bit of the motion, where it's moving through some small displacement delta x. And if we take just a really tiny delta x, notice that the height of the curve doesn't change very much during that delta x. So it's not too bad of an approximation to pretend that the net force is constant, as shown by this flat top of the rectangle there. That's pretty close to the red curve. And so let's pretend that it's constant there. And if it's constant, we can use our good old formula fx times delta x to get the net work done on the object just during this tiny segment. Okay? To do that, what we're going to do is calculate f net x times delta x. F net x is the height of this rectangle. Delta x is the width of the rectangle. So the net work done during this tiny displacement is just the area of the rectangle. And I can repeat that argument for all these other little displacements that happen here and add up the net work in all of those regions. It's going to be represented by the sum of the areas of all the rectangles. We have to be careful to use the mathematician's definition of area. In other words, we would say the area under the curve here is negative because the height of the curve is negative. Okay, so this net force does some negative net work at first, then some more positive net work, then some negative net work, then some positive net work. In the whole motion, to find the net work done, what we do is do the total area under the curve in the math sense, where we take positive area to be where the curve is positive and negative area where the curve is negative. That's something that you might find some use for. You certainly read about it. Let's take a little break.